Thank you, everyone. Actually, I don't work for the Phillies anymore. I work for Thomas now. I worked for the Phillies until last month, so now I work for PyMC Labs. Anyway, welcome everyone to our tutorial. We're hopefully going to learn a little bit about probabilistic programming and how to do that in PyMC. We're going to tag team between me and Thomas, and I'm going to jump between slides and Jupyter notebooks, so please bear with me. Most of these tutorials tends to be folks with a mixed background, so some of you are probably Bayesians already. Some of you probably, how many people have already used PyMC? A third, maybe a quarter, good. And then, others are brand new. So I'm going to make very few assumptions about what people know. I'm not going to talk about statistical theory too much, except where it helps you understand what PyMC is trying to do. So don't worry about if you see math and you're math allergic. It's really just there to support your understanding. So this is just going to be a high-level overview of Bayes and PyMC. So as the title implies, we're going to be talking about probabilistic programming. And the term probabilistic programming is new, but kind of the idea is not. It's really any program that you write that has outputs that are not deterministic, that are not completely determined by its arguments. So really you can do probabilistic programming in principle using any programming language with a random number generator. But higher level languages like PyMC and others, they bring a higher level API to doing probabilistic programming. And really what they do is they introduce what you might call stochastic primitives. So we're used to primitives being things like strings and integers and floats and so on. But we may have other types of primitives in the context of probabilistic programming. For example, you might have a probability distribution like a normal distribution that's a distribution over values, and you instantiate one, and now you can draw numbers from a normally distributed variable. And then you get more complex things like distributions over entire functions, where you realize functions by calling a Gaussian process. We won't get to that in this tutorial, but that's another piece. And then the powerful thing about it is that it allows you to build complex models out of relatively simple building blocks. And you do that via conditioning. So you might create an instance of a variable, call it P, and it's some distribution, and then you'd use that as an argument for another random variable, and it will partially determine what its values are. And the reason that we're doing all of this is it allows us to apply Bayesian statistics really easily to solve our problems and get information out of our data. Bayesian methods, some of us learn it in school these days. When I went to high school and college, they really did not. It's really a kind of a different approach to doing statistics than kind of the classical frequentist toolkit. It's not just a particular method. You can do a Bayesian version of everything. You can do Bayesian hypothesis testing. You can do Bayesian regression, like we'll see today. There's really a Bayesian version of everything. So what is Bayes? Well, when one seeks definitions about these things, you turn to Andrew Gilman very frequently. In his textbook, he says, practical methods for making inferences from data using probability models for quantities we observe and about which we wish to learn. So we use probability distributions, essentially, to describe our parameters, our data, everything. So all the inputs are probabilities, and all the conclusions that you get from these models are also probability distributions. And this confers a bunch of benefits to you, the user. You automatically quantify the uncertainty in all of your estimates. It helps the understanding of the outputs, particularly if you're communicating those with non-statisticians, non-technical folks. Everybody's kind of familiar with probabilities. When we say something's 50% chance, people know what that means. So it makes it relatively easy, a little bit easier to do what you're trying to do. And we use, I've just given you a few reasons why you might do this, but really the reason that we use Bayesian methods is for pragmatic reasons. Some people like it because it's sort of intellectually satisfying. They're not happy with kind of classical outlook on the world, as we'll see in a second. But it really just allows us to do powerful things with our data that we wouldn't be able to do otherwise. So irrespective of the type of statistics that you do, you've always got kind of three things, right? You've got what we call parameters, so things that are unknown, things you're trying to learn about. You've got a bunch of data, hopefully. Sometimes you have more or less than others. And then you tie those together with models, and that's what helps you learn about the parameters from the data. So what's the difference between Bayes and classical statistics? Well, if you're a frequentist, like that's Ronald Fisher in the background, a famous frequentist, you believe your data are random. So they come from some random process generated. When you go out and observe the world, you get new values. They're random processes. And the parameters, the things you don't know, are fixed, right? They're unknown fixed quantities. We can't observe them, and we use the data to kind of reason about them. So they're fixed, and we condition on them. So that implies this sort of thing. So y is our observations, theta is our parameters. We condition on theta, and we say, what do we expect to see in terms of observations or data? So what you have to do is come up with estimators for the unknowns. And this is what frequentist statisticians do. They sit around and they make estimators for things, right? Variables don't come with their own estimators. So a good example of that is if you're trying to calculate like a ratio of something or a proportion, right? This example is what prevalence of autism in a population. You might have a set of kids in a study and you diagnose Y of them with autism, and so that's your prevalence estimate. Well, why do we pick this as our estimator? Well, there's a bunch of properties that they have, right? Minimum variance, and it's unbiased, and a bunch of other nice properties. But every time you have a new problem, you have to come up with a new estimator. If you're a Bayesian, on the other hand, like Bayes, you view things exactly the opposite. So for you, your data are fixed. Okay? They used to be random, but once you wrote them down in your lab notebook or your Jupyter notebook, they don't change. You come back tomorrow, they're still the same values, hopefully, right? So they're fixed, and we condition on those. We consider the parameters to be random. We don't think they're random in the sense that they change all the time. It might be a fixed value that we don't know. But the point is we use probability distributions to describe our uncertainty in those parameters. So we use it in kind of an epistemic sense. So that's kind of the reverse of what the frequentists do, right? So now we condition on the data, and we reason about our unknowns. And this is really what we're interested in, right? We want to know, what do we think the value of theta is, given that we've observed all of these y's? And in fact, it used to be called inverse probability, because you're reasoning from effects back to causes. And the way that we do that, if you're Bayesian, the lucky thing for you is that you have only one estimator, Bayes formula. This is where it gets the name from. Okay, so you have we have a thing called a prior probability involved there, and it describes what we know about all of our unknowns before we collect or see any data. Then we describe our data using a likelihood function, so how our data came about, kind of a data generating process. And then we end up with what we call a posterior probability. So it's what we know about theta after running our Bayesian model, right? The thing I didn't mention is the little thing on the bottom, probability of y, which is kind of a strange thing. So it's the probability of our data, not conditioned on anything. It's not of immense interest, but it's the reason that we have to do all this on a 8-core, 16-core computer rather than on a whiteboard. And that's because it makes the computation really, really difficult, because that denominator is actually the numerator integrated over all of the values of theta. So if we've got one parameter in our model, maybe most of us can do one-dimensional or two-dimensional integration based on what we learned in college. But if you have 50 parameters or 100 or 1,000, it makes the whole thing intractable. And so, skipping a lot of math here, what we do instead is we try to build a model based on the things we can observe, and then we use numerical methods to deal with all of the integration and make sure that everything turns out to be a nice posterior probability. So our responsibility, what I'm going to show you how to do in PyMC, is do things like pick what kind of prior we use, right? We got to pick priors, right? We're going to make choices, subjective choices about everything. So what do we know about our parameter? Well, we may know that it's centered on 0 and varies between, -4 and 4 or something like that. Or maybe we know very little about it. This is another normal distribution. Doesn't look normal, but it is. It's a normal with a standard deviation of 100, so it's almost flat. Or, maybe that disease prevalence problem, we know that it's between 0 and 1, and it's probably pretty low, so we'll use a beta distribution for that. So it involves being familiar a little bit with probability distributions. And then similarly for the likelihood, this is the data generating process, right? So, the likelihood is nice because it contains all the information about our model that resides in the data, and we use that to update the model. So this is Bayes' formula is just a way for formally learning from our data, which is kind of the goal of machine learning, right? So the likelihood function, again, you could have normally distributed data. A lot of stuff is normally distributed. The heights of the people in this room is probably normally distributed. Some of the things are binary or categorical. If you have a certain number of events out of n opportunities, you might use a binomial distribution for that. That sort of thing, okay? I'm not going through all the options here, but that's kind of what we do as Bayesians. And then the probabilistic programming language, it abstracts the inference procedure. So what a good PPL will do is it will separate the business of setting up, specifying a model from the business of fitting that model. And you as analysts are more interested in the first part, right? Probably not interested in how Markov chain Monte Carlo works. We just want an answer to our questions. So, okay. Let me just switch over to some notebooks now. If I can figure the screen out here. Here we go. Oh, that was easy. I need to mirror this, though. Maybe. Let me use the mirror button. There we go. And let's see if how this looks in the back. We good in the back? Can you read that? Cool. So yeah, I'm going to motivate this with a marketing example, some marketing data. So this is something called media effect estimation. So if you're in marketing, if you're in a business, you're interested in knowing the effectiveness of the ads that you buy, where you place them, and how effective they are. And so this comes from a blog post from another PyMC Labs employee, Juan. And there's some details there in the notebook if you want to dig into it a little bit more. So we're gonna import this data. It's just a little data frame of year, month, date information, and then how much is spent. We won't worry about the units right now. And then the amount of sales during that same time period. Okay, and so we've got a target variable, sales, and here we go. So our sales is there, and the media cost is there. I originally called this Y and Z. I'm going to just call them sales and spend. They don't immediately look like they're necessarily related to one another. Thomas is going to solve that problem in detail in the second part of this tutorial. But we're going to go ahead and use that in a regression model, mainly to motivate, again, how you build these models in PyMC. So I'm going to call it sales and spend, and actually, let me clear my output here. And I'm going to start one of the first steps is a little bit of data engineering. I don't have many features to deal with here, so I'm not going to do any feature building, but I'm going to rescale things. I'm going to use what's called a maximum absolute scalar because I want the zeros to be 0 everywhere. I don't want to turn the zeros into other numbers. I don't want it to be the lowest value. So the max ab scalar just scales it by the maximum absolute value. So just a technical detail. So this is going to be a really simple model, regression model. We've probably all built a regression model. You have a linear function. So I've got a coefficient beta and an intercept mu, and that's our expected sales. And then we model the error in that relationship by a normal distribution. Okay, so this, the first step in doing Bayesian inference is writing down your model. And first you write it down mathematically, and then one of the big steps, maybe the most difficult step for some people, is translating that into code. So I'm going to start with something, relatively simple. So we have to decide, well, we've got I gave you our likelihood function. I said the data are distributed normally, so we have a normal likelihood. But that expected value is the function of a mean and a coefficient. So I've got three unknowns here. The Greek letters are my unknowns, make it easy to spot. So there are three variables in this model. So I can't do three-dimensional integration. So I've got to use PyMC for this. So just quickly, I want to dive into what these look like in PyMC. How do we implement these in PyMC? PyMC really contains three sort of classes of variables that are meant to represent everything that you need to build arbitrary Bayesian models. If you can write it down, you should be able to implement it in PyMC. The first is what's called a stochastic variable. And a stochastic variable is one that represents a value that is only partly determined by the value of its arguments. Okay, so give it a particular input, you can't always predict what the output is. It's influential, but it doesn't determine it. So a good example is a normal distribution. You can give it a mean and a standard deviation, but every time you call it, it's not going to return you the same value, right? It's going to be slightly different. A deterministic value, on the other hand, a deterministic node, is going to be one whose values are completely determined by its arguments. Okay? So, for example, if you added two variables together, given their particular values, it's always going to return the same sum, and we always want that. So we're not adding any extra stochasticity in here. Okay? So in PyMC, we're going to start by specifying our priors. We're going to start with the priors, work our way down to the likelihood. Some probabilistic programming languages like Bugs or Stan, you can do things in any order you want because the language is parsed and then compiled. We're writing all of this essentially in pure Python. We got to make sure that the things that at the top of the graph are defined first. So the first thing that we're going to do is define a model. So you can see we have this with statement here, which is a Python context manager. And you may be more familiar with context managers in the context of things like network connections or maybe reading a file, right? So it does a bunch of setup for you, and then it tears things down at the end and cleans things up and exits nicely. We kind of hijacked that approach, and we use it to add things to our model. So we create a model inside the context manager, and everything that we write inside the context manager is added to the model. So I've defined my prior on mu, it's normal, with mean 0 and standard deviation 4. And then my spend effect is going to be half normal. So half normal is a normal distribution, take basically the absolute value of a normal distribution. So it's always positive. So we're not letting the effect of our sales be negative. Very optimistic parameter estimate, or prior here, right? So we hope that it's at least, it's no worse than 0. Okay? And the thing about these variables in PyMC, make sure I run this cell. I always forget to run cells. There we go. These PyMC variables always have to be associated with models. So if I try to run this variable, or try to create a normal distribution just in a random cell, I get an error, and it says no model on the context stack. It's expecting a model needs a place to live, and it doesn't have it. So you got to build these things inside of PyMC models. Once you do, though, you've got this object in here. We've got this thing called a tensor, and a tensor is a data structure inside of another library called PyTensor, which is based on what was formerly the Theano project, which was a library for building neural networks. And we kind of hijacked that project and turned it into a backend for Bayesian inference. And it provides a lot of useful computational advantages for us. So all of the distributions that you get in PyMC are going to be built on top of these sort of tensors. So every distribution that you have in PyMC will at least have this log p method inside of it. Every distribution has to calculate a log probability because that's how we fit our models. Some of them will also have random number generators because we sometimes need to simulate from our model, but for some distributions it can be hard to do. But always has a log p. And so, we can call that log p for a particular value. So this is evaluating the probability of 5 under that mu that's a normal distribution, and that's its log probability. Okay, so we're going to use those as part of the model fitting procedure. And then similarly, if I just want to draw 5 normal values from my prior on mu, I can do that here. If you do just want to use the normal distribution without a PyMC model, you can do that. You just have to use this class method called dist, and then you can draw values from it there. Use it outside of a model, so you can kind of pulls the guts of the normal distribution out without all of the PyMC stuff. And there's a whole, if you look at all the distributions here, we've got anything that you possibly need for your particular problem. They're all in there. And if they're not in there, it's actually relatively easy to roll your own distribution. But everything from univariate continuous all the way up to multivariate models, even time series models, are all there for you. Okay, continuing with our model. So the nice thing about the context manager is, you can open it up, add some variables to it, crack it open again later, add some more variables to it. So we're going to add our sigma. This is the other prior that we need. Oops, this used to be a baseball example, so it was called spin rate model. This should say add span model. And so we've got all of these variables now that are unobserved. Oops, there should be sigma there. I didn't run this cell. There we go. So here's all our unobserved random variables, and it'll tell you what, basically what's there. One thing that PyMC does under the hood is, so if you look at sigma, remember it's a half normal distribution as well, so it has to be positive. So we can't have any negative values for a standard deviation. So, if you evaluate it for a negative number, it's negative infinity, which is 0 probability. Under the hood, what's happening is PyMC is going to log transform those so that they're on the real line. This allows the samplers that we're going to use to fit the model to work a little more easily. And then deterministic variables, my ad spend model here is going to be, that has this expected value, which is just the little linear model here. And so the deterministic variable is always going to return the sum of those variables, whatever their values are. They're not adding any other stochasticity to the model or anything like that. And you'll notice that I didn't give it a name like I did other things. I gave everything names like mu and sigma and so on. This is what's known as an anonymous deterministic variable. So we won't have access to this in the output, because sometimes you have a lot of intermediate variables that you're not necessarily interested in, but you need to calculate something that you are interested in. If I did want to retain this for use afterwards, I can wrap it in this deterministic object, and that gives it a name and then puts it in my output when I need to. And then the last piece here are observed random variables. Now, what's to tell whether your normal distribution is a likelihood or a prior, right? I'm using a normal to describe my mean. I'm also using a normal to describe my data. How can you tell the difference between the two of them? And the only difference, really, there's no notational difference. It's just that we pass the data as this observed argument here. So an observed essentially pins the value of that distribution to the data so that it doesn't change while we're sampling. So it knows that this is data. The other things are random variables. And so I have an attribute in my model here, observed random variables. Those are the things that are informing the model, not the things that we're estimating. And then we use GraphViz in a useful way here so what's happening underneath is PyTensor, the library that PyMC is built upon, is building a graph for us. That's kind of its main responsibility. Build the graph and compile it for us so that we can calculate it. And we can actually look at that graph with GraphViz. So we see our variables here. Unknown variables are circles. And it's got a plate showing that we have 179 observations. Okay, so I've been building the model incrementally, but here's kind of the model all in one place. And I've actually wrapped it in a function because if I need to use it over and over again, I don't make any mistakes. So I can just return versions of this model every time I need it. So everything you saw before is just here. So now I'm going to try to fit the model with MCMC. And I had another slideshow that talks about Markov chain Monte Carlo, but I think we've had enough slides for today. So I'm going to dive right in. Markov chain Monte Carlo is a sampling-based method for fitting Bayesian models. So because of the fact that we can't do multidimensional integration, we've got to do that integration numerically, essentially. And we also can't sample from our posterior distribution because we don't know what it is. So what we do with MCMC is we essentially propose values. The algorithm proposes values, determines whether or not to accept or reject that proposed value, and then it builds up a sample based on that. And so the algorithm, the MCMC algorithms that we're using underneath are kind of doing this sampling for us, deciding how to propose values. And importantly, it relies on gradient information of the model so that it can make good proposals, based on the kind of shape of the distribution. And so pm.sample is kind of Thomas calls it the magic inference button. You just call sample and it takes care of things for you. And I think the developers have done a really good job of making sure that it has kind of useful defaults, but then you can go in and override anything you need in order to make it run better for your particular model, right? So you decide how many draws you want, how many samples you want. You have to let it tune for a little bit. It's got to converge. You got to give the sampler time to adapt to the posterior distribution that you're trying to fit to. So there's some tuning. And then we can do it, we'll see in a second, we do parallel sampling. So you have multiple chains, multiple samples being taken at the same time across multiple cores on your machine. And a bunch of other stuff that we won't dig into here today. There's a whole bunch of, so MCMC isn't like one sampling algorithm, it's a whole class, right? There isn't a bird called a bird, right? It's a class of birds. We have robins and sparrows, but there's no bird called a bird. Similarly here, there's no MCMC, that's just one. It's a class of algorithms, and there's 3 or 4 different ones that are available in PyMC, and PyMC will auto-select the one for you based on what your model looks like and what type of variables that you're using. So there's a sampler called the Metropolis sampler that's kind of an older generation type of, older type of sampler that doesn't use gradient information. And it goes in and every sampler has what's called a competence. And so it's got a competence score. And pass it a normal distribution and it picks the right one for doing that. So what it ends up happening is if you've got binary variables, you get a binary Metropolis sampler. Discrete variables get Metropolis, and continuous gets one called the no U-turn sampler, which is kind of the state of the art, current state of the art in MCMC sampling. And then initial values. So the first thing that you do for an MCMC algorithm is you instantiate arbitrarily, and the arbitrary we pick is typically like the mean or the mode or the median of the distribution in question. And so it'll generate an initial point. This is where the sampler will start. But you can override that as well and pass initial values into the model here. So I'm going to start sampling here. And I've made this sampler intentionally do bad things just to illustrate what happens when things go wrong. I said 500 draws and no tuning. I'm not going to let it tune. And I'm going to start the initial value of mu at -30, which is way out in the margin. And I'm going to use a crappy sampler. And you get a bunch of warnings here about problems during sampling. So you tend to get a little bit of advice from PyMC when you're working on this stuff. When things go wrong, you usually know. And then there's a companion library called RVs that was initially spun out of the PyMC project, and it is the home of all of kind of the diagnostic utilities, plotting functions, the backend that holds all of the output from MCMC sampling. And the nice thing about it is that it is platform agnostic. And by platform, I mean which probabilistic programming language you're using. So you can use it with Stan, you can use it with NumPyro, whatever you want. They can all be converted into this backend. So I'm going to use it here to plot the trace. So the trace is just the set of values from the model, and this is not what you want it to look like. So remember, I started it all the way out at -30, and you can see that it's trying to find its way back up into the region that it's supposed to be at, but it's not there yet. So this was deliberately bad, and this model needs a little bit of tuning. So if we run it properly, now I'm going to give it 1,000 iterations to tune. Works pretty quickly. No error messages this time. Okay. And now if we look at the posterior distribution, this is our posterior estimate of mu. So the mean is around 0.84. You get a little, the HDI stands for highest density interval. So it's essentially the narrowest 94% interval of values. So it kind of shows your uncertainty about that variable after you've shown it the data. And then we have the same thing for the other parameters. And as I said, RVs gives us our backend, our sort of database, if you like, of output. And you get this little table here. So this is, RVs has this inference data object, which is essentially an extension of the X-array library, if any of you are familiar with that. And this gives us labeled arrays. So this contains all of our posterior samples. You can see the names of all of the variables in here, all of the dimensions. So you can see that it's sampled. Remember, I told it to take, what I say, 1,000 draws and 1,000 tuning. It doesn't save the tuning. It throws those away. They're not of interest to us. And then it saves 1,000 iterations for inference. But I used 4 chains, so I actually have 4,000 draws. And they're all stored in here. In fact, you click on the little database icon, and you can see the actual values here. And then a bunch of other information, even a copy of the observed data that we used to fit the model. So it's all there. And you can store this as a JSON or a netcdf or whatever you want here. And yeah, so parallel sampling, as I said, you can't buy a machine without multiple cores anymore. And so PyMC will use this. I think by default, it takes half of the available cores. And then you can determine how many chains you want and how many cores. So again, if you pick 4 chains, by default, it's taking 1,000. So it even tells you down here, 4 chains and 100. Oh, I took 100 this time. So I'll end up with 100 values. And so here I've got 4 by 100 samples. And that's what we're going to use for inference. Okay, so there's kind of 3 steps to Bayesian inference. There's specifying your model, writing it down in Python or R or whatever you use. And then there's calculating the posterior distribution, which we've done here with MCMC. And then the third step is checking the model. And this is very important because your model is just a big hairball of assumptions. And you can generate nice-looking results, pretty simulations from MCMC, and have absolute nonsense in the output. So there's 2 types of diagnostics you have to do. You got to do some convergence checking. Did my model run as we expected using MCMC? So it's very obvious in that first example that things were bad, but you want to make sure that MCMC worked properly. And then goodness of fit. Does my model fit the data? Does the data look like it might have come from a model like this? So it's kind of 2 steps. First one is kind of, it's kind of hard to absolutely determine convergence. And so I'm going to run this model deliberately poorly again. And I get even more errors, so I know something's wrong already. But the first thing you want to do is kind of stare at the trace. And you can see here, again, these don't look like nice, neat distributions. Each chain has its own line here. So, the 2 lines not fully overlapping is a bad thing. And then all these weird black lines here, each one of those is trouble. Those are divergences, and we'll talk about what those are in just a second. Conversely, if I look at the model that fit well, the previous one, you see each of the 4 chains, they look like they did approximately the same thing, right? They all look like normal distributions. And then you get what we technically call the fuzzy caterpillar over there on the right. If it looks like a fuzzy caterpillar, that means that A, it's stationary, it's not weaving all over the place, it's homogeneous, it's not varying in widths and so on. It just looks nice and fuzzy, as we like it. And then you noticed up here it said, warning, there were a lot of divergences after tuning. Increase target accept or reparameterize. And divergences are is what happens when things go bad with the sampler. As I said, it uses kind of gradient information about the model, and it kind of, it's almost like a skateboarder in a skateboarding park. It kind of roves around on the contours of the landscape that is the posterior distribution. But every now and then, the skateboarder takes a turn too fast and goes spiraling out of the park into the parking lot. And that's what happens here. And you can see it's trying to trace this sort of funnel shape in the posterior distribution. And it's doing an okay job here, sort of an okay job here, but here it kind of spins off into the wilderness and it diverges. And so those are problems, and PyMC will tell you when that's a problem. There are two things you can do. You can make MCMC try harder. You increase the target acceptance rate that it's higher, so it'll essentially take smaller steps. Using the analogy again, the skateboarder will go a little bit slower and kind of do a better job, but it's more computationally intensive to do that. What it usually means is you've kind of misspecified your model. You've made it difficult for the sampler to do its job, and so there's usually some way you can reparameterize your model to improve that. And if you see one or two divergences here and there, it's not a big deal. But once you start seeing thousands of them, and they're all kind of concentrated in the same place, it's a problem. Kind of the go-to, sorry about the math here, the go-to diagnostic for convergence is something called R-hat. It used to be called the Gelman-Rubin diagnostic. And really what this is doing is it's doing kind of an analysis of variance of your samples, of your trace, right? Remember analysis of variance, right? You compare, you're trying to see if groups are different from one another. You do the same thing on the trace. So you got these 4 chains, they're all sampling at the same time, and it compares the variance within the chain to variance between the chains. And if you've converged to the same place, you shouldn't be able to tell between chain from within chain variance. And so the ratio, as n gets very large, you're kind of, one of the guarantees you get from MCMC, from any MCMC algorithm, is that you're guaranteed convergence. What they don't tell you is how long it takes, right? So there's no rule of thumb. You could be waiting for days, weeks, lifetimes. So you want to monitor things like this. When R squared is approximately 1, you're happy about it. So and those are reported here. So RVs has this summary function that tabulates things. And you see here R hat for these is all 1. And so we're happy. Okay, goodness of fit is a slightly different thing, right? Again, you can do really great MCMC work and then end up with a model that isn't very good. So goodness of fit, as the name implies, is it checks to see if the fit is any good. And so by goodness of fit, we mean, does it fit, does the model and the data look similar? And for that, we use something called the posterior predictive distribution, which is another scary integral. But the good news is we don't have to worry about doing any integration because we've already got all of these pieces. F on the right there is the posterior distribution. Remember theta given y is the posterior from my slides. And then y tilde, our new data, y tilde given theta is the sampling distribution. So all I'm going to do is essentially draw samples using a random number generator from our posterior distribution. And I'm going to get essentially replicates of my data, right? Simulations from the model. And I compare the simulations to the actual data. So I can do that for my model. It's really fast. There's no more model fitting that needs to be done. It's usually really fast. And so now inside my trace, I've got this posterior predictive bit. And then I can plot it. And plotting takes longer than the sampling. And so the black line here is the data, and each blue line is a generated data set. And so, if the black line was blue, you wouldn't be able to see it. So you can kind of say it's a pretty good fit, right? The data kind of falls right in the middle of all of the samples. So that's a really relatively decent check, okay? So what does the model look like, right? Our little regression, trying to predict. Remember, we've probably forgotten what we're trying to do here, right? We're trying to predict sales from spend. And so this is it. Ta-da! It's terrible. There's no relationship whatsoever. So posterior predictive mean is the green, and then the actual target is the black line here. And this isn't surprising, right? Just because I sold 50 ads today doesn't mean sales today is going to be good. It probably takes a little time. There's trends, there's seasonality, a bunch of other things. And I'm going to let Thomas drive it home and make this model work.
Questions?
And we actually do have time for questions because I skipped my slides. So while we're switching computers, you can ask questions if you've got them. You have your own microphone, right? Yes, sir.
Yeah.
Oh, sorry. You go on this side. Yes.
Hi. Is there any reason why you wouldn't pick the no U-turn sampler?
There is. So I mentioned that it uses gradient information to do a good job of sampling. And you can only take gradients of variables that are continuous. So if you have discrete variables in your model, you can't do it. So what PyMC does is it does a hybrid. It'll use the Metropolis sampler for the discrete ones and nuts with the other one. And there's no real theoretical justification saying that that's good, but it generally works okay. Better thing is to integrate out the discrete variables, and we're actually working on ways of automatically integrating discrete variables out, but that's usually the only time you can think of that you don't want to use nuts.
Yeah, excuse my ignorance with the question, but I'll ask it anyway. Was there any reason why mu you use a normal distribution and the other two parameters you use a half normal distribution? Was there any intuition behind that, please?
Yep, that's probably the hardest thing about doing Bayesian inference is picking priors. The specific reason we chose it there is that the mean of a normal distribution can be any value on the real line, and so it's an easy distribution to work with. It's symmetric. You can make it as wide or narrow as you want, depending on how ignorant you are about that value. The half normal is constraining things to be positive. So sigma is a standard deviation. So you can't have negative standard deviations. And then my subjective prior for the beta was that sales would be positive, have a positive effect, that spend would have a positive effect on sales, which it's not always the case. We hope it's the case. So yeah, misspecifying your prior. You don't worry about it too much, but you don't want to make a really bad choice. Like if sales really were negative, then this model would be screwed because there'd be no way. Once you say something's zero probability, no amount of data can turn it around. So, but yeah, good question. It's not an ignorant question at all. It's prior selection is a tough thing, particularly as your model gets more complicated and it's less intuitive as to what you need to do.
Thank you.
Yeah.
I have a similar question, just following up on that. It's probably more of like a statistics question than programming, but I'm just curious if there are like systematic ways to choose those priors and like how much kind of guess and check that involves, or if there's like a process, or is it just really like you do this enough and you kind of get a sense of which ones to use, and then I guess like after that, is there a way to evaluate which ones are working better than others? And
Yep.
Yeah, how does that kind of work?
So Thomas is going to talk about the Bayesian workflow, and part of the workflow is it's a great question. You fit your model, and when you reach this, it's like, oh crap, my model sucks. And so then you go back to the beginning and you reevaluate your priors, you reevaluate which variables you included, and then you change them. In terms of prior elicitation, you kind of guess at it. Sometimes priors are nice because you can add domain knowledge explicitly to your model without having data, which sounds like cheating, but there often is data. You're doing a biomedical study, there's probably reams of data about what a parameter value should be for whatever it is you're doing. And so you can construct a prior based on like the population of existing studies, kind of like a meta-analysis or something.
What you know about the parameters gets kind of encoded in the distributions that you select.
Yeah, she said that knowledge gets encoded in the prior distribution. That's the idea. You're supposed to encode that. And the more you can constrain your priors, actually, the better your model performs. It's like constrained optimization is always easier than unconstrained, right? So yeah, thank you. And is there more? Or,
Let's do a couple more questions, sure.
Okay,
Yeah.
couple more.
How does the inference time kind of scale as a function of the number of parameters in your model typically?
How does the what scale?
The inference time
Oh, time. It depends on what mode of inference you're using. For Markov chain Monte Carlo, things scale relatively well for the size of the model in terms of numbers of parameters. It typically doesn't care too much about that. It scales very poorly with the size of the data. So traditionally, because at every iteration, when you run 1,000 iterations, it's got to assess the log probability for every data point, right? And so that's kind of the constraint. And so, we try to come up with more efficient MCMC algorithms, like Nutch is way more efficient than Metropolis. And then we then try to use brute force, right? So we use the JAX backend and use GPUs and stuff to accelerate those samplers. And there's only so much you can do because it's a sequential algorithm, so you're always just working on the current sample. But so really, it's data that's the bottleneck more than the size of the model.
Thank you. Yeah, thanks for the talk. Super cool. Spitballing here, I'm a Bayesian statist, not really my area. Could there be an argument that in this particular context, more recent sort of data could be more informative, and so you could put a larger weight on more recent data, and then a con to that could be that you're potentially sort of undermining the belief of stationarity in your data. Is that an approach you could take?
Okay.
Yeah. So we're going to see that at the end. So it's a great question, and these are exactly the type of things that we're going to go into in the practical session. But thank you.
Nice.
Cool. Cool. Well, let's give it up for Chris. All right, yeah, thanks. That was amazing to have all the foundations set up and some of the theoretical building blocks, and now we can really dive into the practicalities and see, for me, what the true superpower of Bayesian modeling is. Who here does machine learning on their problems? Okay, yeah. So it's a super useful, powerful tool, and I'd like to contrast Bayesian modeling a little bit with it because the whole philosophy behind it is quite different. So with machine learning, right, you have your data, and you then fit a model, and the model really infers almost everything it can from the data, right? So that's why having a lot of data is really useful, because then you can build a really complex model that estimates some crazy hyperplane, right? But with Bayesian modeling, you take a much different approach. You really think carefully about your data, your problem, and critically the structure of your problem, right? Like, how do those variables that I have, how do they fit together? And then you encode that knowledge you have about the causal graph of these different variables into a model. And then you see how well does it explain the data. And then, in this case, right, we see maybe not that well, right? And then we start to think about, well, okay, what structure is my model missing? And then you experiment, right? Then you improve that model and add that one thing. And then you look at it again and you see like, oh, well, now it fits this aspect, but maybe not that other aspect. And this iterative approach and the automaticity given by these tools, where you just build a model in Python code, and then you just hit the inference button, right? And then you see the results, you just keep improving the model. That, for me, is like really the true superpower of this approach, is that it allows you to build custom models that encode the domain knowledge into a model, and then very iteratively and freely explore different ideas you have about the data. And during this process, not only do you build a really cool statistical model that then is like often much more accurate if you map this properly, but also you learn something about your data, right? By really like diving in. So it's really much more part of the data analysis part than just like the machine learning black box piece. So let's start here, right? So this is where we left off. We have, over time, the sales in black, that's what we wanted to model, and then we have the predictions of the model in red, right? And then in the background, we have the uncertainty about that. So this is like, obviously, the other thing that we get is we get uncertainty in our predictions, but here, let's just focus on the red line for now and see, is that a good fit or not, right? So Chris already gave away, and it's pretty obvious that it's not that great a fit, but why? What is missing? So anyone want to like take a look at what properties the black line has that the red one is missing. Seasonality? Yeah. So we see that this black one here has a cyclical pattern in it, right? That this one isn't matching, right? It's just like a flat thing. So seasonality is a great one. What is another one? Trend. Perfect, yes. So we see not only does it have this cyclical pattern, it also is slowly drifting upwards over time. And this red line, which is really just what the model is able to do, can't support that. And of course not, because it is just a linear regression model, right? We just say we have x times beta and then plus intercept, and that's the output of it. So it has nothing about time or seasonality or trend. So now let's enhance our model and include those. So how do we do that? There's multiple ways of doing that. If you're more advanced, maybe you're thinking Gaussian processes. That's like a class of things that is like really cool. Here we're going to do something a little bit more simple, but nonetheless very powerful. So these are ideas that actually come from the profit model that Facebook released a couple of years ago. And we're just going to do some feature engineering. So we're going to engineer a feature for a linear trend. So here, all I'm doing is I just sort of get the length so that over the time period here, from the start to the end of my time period, T is just ramping up from 0 to 1 in terms of the sales. And then what I want to do is, right, I have this linear trend component. What is the coefficient that I need in order to match the trend I have actually in my data? So here I'm plotting two coefficients. One is just 1, so then it's just going to go from 0 to 1. And one, if I choose the coefficient 2, then it'll just like rise quite double as fast. So that's the first feature. The second feature is one for seasonality. Here we're doing something very related to Fourier analysis, where we're using a whole bunch of sine and cosine functions, and out of those we will do something similar to this linear trend here. So what I'm doing here is, and by the way, like some of the code is like a little bit longer, so you don't expect to like understand everything. I will always just like point towards the things that are like important and that I want you to understand. The other stuff you can just like ignore. But all I'm doing here is I'm just creating different sine and cosine functions and adding those to a pandas data frame. Really, the important thing is what we're going to look at here. So these are all the basis functions that I have generated. So you can see for sine, we have some low frequencies, some high frequencies. For cosine, the same. And what that allows me to do now is to, again, have different coefficients for every of those basis functions, and then from that generate all kinds of seasonal patterns. So here I have two different ones I generated with just random coefficients. So I'm just, so I have 14 basis functions, 7 for sine, 7 for cosine. I just multiply them and sum them, meaning I take the dot product between my Fourier features and just the random coefficients, and then I get, for example, this, right? Or if I execute it again, I get something different. And the two lines are just two different random coefficients. So just with this, I can generate all kinds of cyclical patterns, which is a pretty simple but elegant and powerful way of modeling these seasonal patterns. Now that we have these features, we're going to integrate them into a model. And we're going to do that in a very similar way to before, where before we just had a single covariate, which was the spend data. By the way, in the slides here, I renamed it to cost, so spend or cost. How much do I spend on my media, right, on any given day? Now I also have a linear trend component, and I have the Fourier coefficients. So it's just adding more terms to that linear regression. So here is the PyMC model. I have my intercept. So again, I have my model context. Here I'm using coordinates. These just allow you to specify the dimensionality of your model, right? So if you remember, we have, for example, 14 Fourier coefficients. So that means for every one, we need one coefficient. So I could just say shape equals 14, but it's a bit cumbersome. So we have this feature called coordinates, where you can specify, and then automatically PyMC will infer like, oh, okay, you already told me that there is this dimension called Fourier coefficients, so I'm going to do that. It's not that important, but it's a nice addition. So here now we have our priors and our parameters. We have the intercept, that was a normal distribution. We have now a coefficient for the linear trend component. Again, that's a normal distribution. And then for seasonality, we have a Laplace distribution. We give it a name, a mu and a b. B is similar to sigma. It's also related to the dispersion of that parameter. It's not the variance, but it's related to it. And then here I'm passing in the DIMS argument. And that just says, okay, this is not just a scalar value. This is actually 14-dimensional vector. And then I have the regressor before that estimates how strong is the effect of my cost, my spend on the sales. And then I have the sigma, my error term, that's a half normal. And then now the other thing I'm going to change is that before we were using a normal likelihood, I'll come back to that. Before that, I want to talk about the Laplace distribution. So what is the Laplace distribution, right? It's a good idea when you are dealing with priors, right? And a couple of questions already came up with like, how do you choose them? Well, one great way is to just plot them. And the easiest way to do that is to call the pm.draw function. So that just says, okay, from this prior distribution, draw 1,000 instances. And then we just plot the histogram, and that tells me what that distribution looks like, right? Because, I mean, I can't think of like exactly what these different parameters relate to in terms of that. But once you can look at it, then you can actually see like, oh, does my prior cover the range of parameters that I expect, right? And that's really the logic behind priors, is oftentimes you have some knowledge of the scale of the parameters of your model, right? Like starting very simple with variance. We know that it has to be positive, right? That's a simple one. How positive? Is the variance going to be 1 million? Probably not, right? It's going to be close to 0. So this is how you start to think about these things. And there's other ways of doing that elicitation. But here I'm just now plotting the distribution, the prior distribution for my Fourier coefficients. So you can see, because I specified the DIMS argument, that I have 14 of these. And they all have the same Laplace distribution, so they're all on top of each other. And you can see that this does not look like a normal distribution. But rather, it's much more peaked. So anyone want to guess why I chose this distribution and not a normal distribution? Yeah, he said, I want to induce sparsity. That's exactly right. So as you can see, this distribution says I really like values very close to 0. Yes, you can deviate from 0, but I'm going to make it harder, right? It's going to say, like, in the absence of information, in the absence of strong information to the contrary, we want to like say it's 0, very close to 0, exactly 0. And that's what that is. If you're familiar with ridge regression or lasso regression, that's the same concept, right? You want your coefficients in lasso regression to be exactly 0. You want a sparse representation. And there's actually mathematical equivalence between using Laplace prior for your coefficients to lasso regression, and a normal distribution is the equivalent of doing ridge regression. So that's just an example of, I could have used a normal, right? That would have probably also worked, but I get smaller values. Here I want to say, okay, well, most of the coefficients are probably going to be 0, but some of them are going to be larger. So I have this heavy tail. And now we come to the second part of the model specification, which is how do those things link together? So here now I have my trend. So I just say this is a deterministic, right? So this just allows me to now recombine things and give them new names. So random variables get combined in a deterministic way, and I just give them a name. You don't have to use that deterministic thing, but it allows me then to later look at it in the trace of my model. So here I'm just saying, okay, I have the intercept plus my coefficient for the trend times t. And t was that linear feature I created in the beginning. And I have that across all dates. So this will be for every data point, right? For every day, I will get one output. Seasonality, the same. Here I'm now using the dot product because I have a matrix. And my Fourier coefficients, these are the Laplace ones. And then the cost effect is just the coefficient for my cost, B cost, and the data, right? How much I spent on my marketing on every day. And then we're putting all of those things together by just adding them. So we have the trend, we have the seasonality, and the cost effect. All these together now add up to the mean of my prediction. And then that mean of my prediction, I plug into my likelihood function. Chris used a normal likelihood function, which is a great choice if your data is normally distributed. Oftentimes, maybe the data is more noisy, right? There's like outlier values. In that case, it's quite convenient to use something that has more mass in the tails. So normal distributions are notorious for having very little mass in the tails. A student t-distribution allows you to just have values that are far away. And that makes inference oftentimes a little bit more stable. So here I'm using a student t-distribution, and that has that additional parameter nu, which specifies how much mass there's in the tail. So we also estimate how likely outliers are in this data. And then I just plot it. So now we can see we have added a lot of structure now to our model, right? So we have the cost, our data, that we multiply with the cost effect. We have the trend that comes from the multiplying our feature with the trend. We have our intercept, we have our seasonality. These are the 14 Fourier that are Laplace distributed. That goes into these nodes. These are my 3 deterministics that come together into the mean of the prediction, and then that goes into my likelihood function with the parameter for the tails and the parameter for the standard deviation. So yeah, now we added that to our model, and now we just do the Bayesian workflow, right? So first, we just want to simulate from the prior predictive. So without actually being concerned with the data for now, we just want to know what patterns of data is my model capable of generating. And this is usually a great first step, because there you already see certain things. So here, this is what that looks like. So I do plot it with the data together, and in the background is the prior predictive, which is just, yeah, all the patterns that my model is able to generate. And you can see it can generate like basically patterns from -20 to 20. So y-axis here is the sales, and x is the time. This looks okay, right? We could now say like, well, maybe this is like too general, right? Like sales are much more constrained, right? So I don't have to have it generate values that are like all the way up here. And actually also, I mean, there's another important bit of information that I'm not encoding here. Anyone want to take a guess? What patterns in the data is it generating that I probably would not expect to see in reality?
Sales can't be negative.
Yes, exactly. The sales can't be negative. So, but clearly the model is able to generate negative data. So we're not going to fix that here. It would not be that hard. We could log transform the outputs or choose a different likelihood function that is only constrained to be positive. But we're going to roll with that for now, just for simplicity. Now we move on to posterior sampling. So here I'm calling the pm.sample function, as you've seen before from Chris. And we're going to do some things that are a little bit more advanced here. So we're going to pick a different implementation of the NUT sampler. So NUT is our workhorse. And because it is like the sampler to rule them all, we have different implementations of it. And NumPyro is another amazing package for doing probabilistic programming. And they have a sampler written in JAX, and you can run PyMC on the JAX backend as well. And then all the sampling is happening on JAX, and you can run that on the GPU, and it's just much, much faster than anything else. So that's just it gives the same results, but it's just much faster. And here is another one that's not as important, but I want to save the likelihood values, because later on I want to compare those models. And then I'm sampling from the posterior predictive, right, to see, is my model doing a better job now fitting the data than before? The next step in the Bayesian workflow is model checking. So we sampled successfully. I can just show you how quick that runs. We sampled successfully, and now we want to, and it's done. So very quickly using the Jack sampler. Now I would just want to look at, does that make sense? So I have the mean values here. The first thing I probably want to look at is the R hat to have my chains converge. So these are all 1, which is where I want them to be. Next, I want to look at the caterpillar plots. What do my posteriors look like? We have our posterior distributions here, the histogram of them. Those look nice and well-behaved. And then here I see these nice, stable caterpillars where the sampler over time is not like walking around or doing anything crazy. It's just sampling very stable from this posterior distribution. And here we see for the Fourier features, right? This is not just a single one, but 14, so we have 14 individual distributions. And we see that effect of the Laplace, right? So some of them, like 2 specifically, are like quite strong. Those are the most active ones, but most of them are very close to 0. So that's, if I have chosen a normal distribution, these would probably be a little bit more, still clustered around 0, but maybe not as much. So that worked nicely. And yeah, then I can look at the posteriors on a single axis and maybe start interpreting these parameters. But the main thing that we're going to look at now is the posterior predictive samples generating this plot. So you feel we did better this time? Yeah, I agree. So that's great. So we matched the data much more closely. The seasonality and trend component really helped us here. And now, well, we just keep iterating this workflow, right? So this is what we're going to keep doing. And for that, we're going to look at different ways that the model fits the data. And so this is just one way, right? We just like directly look at the data and at the predictions, and we see visually, okay, this is kind of cool, but there's different ways of looking at different components of this. So another way of doing that is, before that, here is a cool way of also thinking about the model where we can decompose these things, right? And this is really the power of Bayesian modeling as well, because now that we have this model that we have handcrafted, we can also really dig in and understand the individual contributions of my pieces, right? So if we really want to learn and generate insight, well then this is going to be really helpful because I can really look at, so I have the target data, the sales in black, I have the linear trend with intercept in red, so you can see, okay, cool, this is like capturing this aspect of the data pretty well. Then I have my seasonal component over here, and then I have the cost effect in blue. So if I add this line, and the red line, then I get essentially the prediction from here, right? But the idea is, yeah, now that we have that, we can decompose things and really learn about the individual aspects of our model and dig in. Okay, now I come back to different ways of looking at how well my data fits, how well my model fits the data. So here's another way where cost or spend, right? How much did I spend on my media over, and now we're losing the time component, right? So we're just like every data point here in red is a data point, is a day where I spent, and then how much sales I did on that day. And then I plot the prediction of my model. So this is just another way of looking at it, and you can see, okay, well, we're not really doing such a great job modeling it here. There's a couple of things we're missing. And one of them is where also now we can inject some knowledge about the problem. So anyone here who works in marketing analytics? So if you were, you would know that if you spend twice the amount on Google Ads than you do, that your sales do not double, right? There's a saturation effect that kicks in. So you can't just like keep cranking up more and more marketing spend and expect things to just like linearly increase, right? There's a saturation effect. And that's something which we are not modeling here, right? So far everything is just linear. And then there's another thing also that I'm gonna show you. And here's yet another way of looking at it to see where our model falls short. So here I'm plotting over time now the effect that my spending has on the sales. And again, green is my is the data, right? So you can see here over time, like on this day, my media spend has like a really large effect, right? And here it actually has a pretty small effect. And my model in blue is not really doing a great job matching that, right? So the model here is over time just constantly sort of predicting things, where here the effectiveness of my marketing is going down, right? So over time, we observe in the data that even though I still spend, the punch of that is diminishing. And we can think about why, but we definitely see that our model is not capable of doing that. And obviously not, because there's no concept of time, right? It's just a linear regression. And there was this question that you had about like, well, what about more recent data, right? Doesn't that influence things more? And the answer is, well, yeah. So clearly things that are still missing our model, and we're just going to keep iterating. So as I mentioned, there are two things that are commonly added to these models. And now when we add them, that's what really gets us into the domain of what is called a media mix model or marketing mix model, MMMs. So you might have heard that before, which is a model to allow you to estimate the effectiveness of your marketing, right? So you spend all this budget on Twitter ads and Facebook ads, and at the end you only observe how much sales, and from that you want to back out. So you have to take into account all these complexities like saturation. So in order to do that, we can just apply a logistic saturation function. This is the math, and for now we're just going to look at it. So here, as we increase cost, we're not just going to linearly scale sales, we're going to plateau, and that function has a parameter lambda that says how slowly or quickly I'm saturating my media channel. Does that make sense? And the other thing that I want to include is an ad stock effect. And what that is doing is when I spend, so this is over time, I have 2 points where I do marketing, so this is a different example. And here I'm looking at a measure of my sales. You can see that on that day where I like blast a lot of, say, TV ads, there's a lot of sales, but then the next day after, there's an aftermath, right? There's a fact where people still like sort of had it bumbling around in their head. They're like, oh yeah, I saw this ad yesterday, let me check out the product and lead to a sale. And then over time that diminishes. So there's this time-dependent effect that we want to, and that is called ad stock, and we want to model that as well. We do that with a convolution. I'm not going to go through the math here, but you can probably imagine, yeah, we just like sort of fit that, fit an exponentially decaying function to every time we like have marketing effectiveness, and then these get added over time together. So I'm defining both of these in a way that PyMC understands, and then I just now take my existing model and I keep adding that structure, right? This is now the next iteration in my Bayesian workflow. So here, everything actually stayed the same. I haven't done anything here. And now I'm adding 2 parameters. One is a parameter for my ad stock effect called alpha, and then the saturation effect, how quickly does that asymptote lambda. And I'm giving both of these priors, as I always do. Alpha is between 0 and 1, so I'm giving that a beta distribution. And then lambda is a gamma distribution, which is also positive and gives more probability to lower values. And then I'm, again, plugging things together, where now, like, this is the same as before, and then I'm punching that through my ad stock. So here I'm just, that geometric ad stock function that I defined, I'm passing in these values, and then the output of that ad stock convoluted output, I'm going to pass through the saturation function. So yeah, just more layers to this, right? Like in neural networks, you have layers. So here we have a similar concept where we just like keep transforming things until they are in the space where we want them. So now, again, the model has gotten more complex. You can see we have the ad stock. So our cost data is punched through the ad stock, and then the saturated, and then comes to the cost effect, and then the rest here is as before. And then, well, we just follow our Bayesian workflow. we do prior predictive sampling. This looks fine, right? The model is able to generate data similar to before. And now I'm just doing posterior sampling. Quickly, the R hats, now I'm doing model checking. The R hats, they all look fine. That's cool. And now looking at the trace, there's two things that I want to pay special attention to, alpha and lambda, the parameters of my add stock and saturation. And adding these to the model has not impeded the conversions. So still, I see that the model is converging just fine, and these two parameters I estimated pretty well. And also, just as an aside, I mean, these MMM models have been built for decades, but they have been in a very manual way. So, and what people had done before were basically, because they didn't have these fitting tools, they would just handpick alpha and lambda values until they sort of found something that worked well for them. So this is another power of this approach, is not only can we build these rich models, but with these powerful sampling algorithms, we can just, anything we don't know, right? We don't have to like hand fiddle. We can just hit the inference button and it'll work. And really we're just scratching the surface here in terms of how complex these models can be. We can look at the outputs more, and then the posterior predictive samples. This looks, I guess, maybe even a little bit better than before. But what we're really interested in is this other plot where we saw the mismatch between them. So here now we can see the predicted values as blue dots and the observed values as red dots. And looks better, right? But not quite right. So we're still, even though, yes, we are like saturating, as you can see here, we're still like not really providing a great fit. And why might that be? Well, if we look at this plot, we see that we still miss this non-stationary effect, right? So yes, we have saturation, which helped some, but the fact that the media effectiveness is going down over time, as we're clearly seeing here in the true data, the model is still not capturing, because it doesn't have any structure to capture it, right? Like all we did was add saturation in that stock, but nothing that allows it to say that the effectiveness of media is changing over time. It still has no concept of time. Which obviously raises the question, how do we include that in the model? So that gets us to our last section where we can add that. Before that, I just wanted to give you a small intermission where you can see that things have gotten quite complex here, right, in terms of the model. And for the type of models where we so this is quite a lot to write, right, and to maintain. So if you keep doing the same model all over and over again, right, and the whole industry is using these MMM models, so that's why we released a tool called PyMC Marketing that is also open source, that allows you to build exactly the type of model that I showed you manually now. Instead of like having like all this complexity, it's just a single line, and that builds the model for you. So here, instead of doing everything I did above, I'm just doing from PyMC Marketing import MMM, and then I'm instantiating the delayed saturated MMM, so delayed, right? That's the add stock, saturated, that saturation effect. I pass in some specifications about my data. I have seasonality, I have the lag effect, and then I just call the fit function here, and that already sets up the right sampler and everything. So it's just trying to be as simple as possible without having you to really like build everything from scratch yourself. A couple of warnings. And then we also included all kinds of different plots, like the plot that I already showed you, the components distribution. There's like a waterfall plot that shows you which component contributes how much. You can plot these saturation curves, right, that are estimated. So just making it simpler to do so. But the main focus here is on PyMC. I just wanted to show you that if you're interested in this type of model, this is a good, easy way to get started. Okay, so now for the last iteration of the model, we're going to look at time-varying parameters. So what we want to achieve is that in the beginning, the media effectiveness is higher than in the end of my time series, right? That's clearly the pattern we saw. And one way to do that, there are several ways to do that. one simple way to do that is to use something called a Gaussian random walk prior. And I'm going to show you what that is. First, we're just going to code it up. And here, so this is everything identical to before, right? You've seen this. These are just the priors. And now I add another prior, which is here called a Gaussian random walk. And that is a little bit of a more complex prior, but it really allows us to dive into and model time-based, time-varying things. And the parameterization is similar as before. I have a parameter, I have a name, I have a sigma parameter, and that's really it. And then I have to say, like, this is across dates, right? So for every day, I want a different value. So what is the Gaussian random walk? Mathematically, it's actually quite simple, even though for me it took a second to sort of grok it. But what I'm saying is, I have a normal distribution centered around xt, and that is distributed according to a normal distribution centered around the previous value. So you can think of this as saying, okay, now today I'm at 1, and then what's the value tomorrow going to be? Well, it will probably not be 300, right? Or it's probably not going to be -20. It's going to be in the vicinity of yesterday's value. So it might be 1.2 or 0.8. So that is really the logic of that, is you have, you draw a new value based on the previous day's value in that vicinity, normally distributed. And again, when we're just want to understand our priors, an easy way is to just draw prior samples. So here I'm drawing, again, I'm just calling pm.draw of my slopes. That's the Gaussian random walk, 5 different ones, just to take a look, just to get a feel for them. And now we can see, yeah, so this is over time, right? So I have 180 data points, and for every time point, I get another parameter value, which relates to how effective my marketing is. And I can see that this is now changing over time, right? So this is exactly the type of thing we want. And it's not just like random values, right? It has structure. It is like gradually changing over time. That's really the key information that I'm injecting with that prior. So we can see, yeah, this is like just meandering around, and different instantiations give different ones. But yeah, it has that time-dependent structure that I want. So I'm just trying a couple. This one went really crazy. And I'm taking the exponent of that just because I want those values to be positive, right? Because I think that my marketing effectiveness is going to be positive. So this is really a really cool trick. Like any model you have that has a time-dependent component, you can just replace your parameter to be this Gaussian random walk and then have it time-varying and model the thing that you asked before. And then the model actually is very similar to before. So really the only thing that I'm adding is that I multiply the Gaussian random walk with the output of the saturated function. And then I'm doing the standard procedure. This looks similar. I'm doing posterior sampling. My R hats are all really nice. This one is a little bit elevated, but it's actually still within reason. But now we're like starting to make the sampler work a little bit harder here, right? The model is quite a bit more complex. And now I can look at the posterior of that effectiveness. So over time now, I'm looking at that time-varying parameter, and you can see it's that rope here, right? So now it's basically similar to what I looked at with the prior, right, which had just these meandering lines, but now they're the lines that are best explaining the data pattern I have, right? So before it was the prior, now it's the posterior. And you can see what we already inferred from the data, that over time, we see that the effectiveness is going down, and that's what we're seeing here. And for the final model validation, did we actually model this? So now here, we can look at, okay, that actually does match very well with the data points, so that has helped here. And looking at things over time, we see now the model in blue is able to model the effect that the media effectiveness is decreasing over time, modeled by this Gaussian random walk process. So with that, I'm happy, right? We have a model that really matches the data. We went through a couple of iterations, seeing where the model mismatched, improving it, and now having something that works quite well, samples, we can infer, we can understand, and answer business relevant questions. So yeah, that's it. We can do model comparison, just saying, okay, which of those models is the best? Not surprisingly, the time varying model, the last one I showed you, comes out on top. And if you want to know more, with PyMC Labs, we're building these types of models for customers, not only in marketing analytics, but wherever you have a problem where you think Bayesian models can help, to help you through various ways. One is just through consulting, helping your data scientists build these models, and also through training. We do corporate training workshops, and there's also a self-paced individual learning course that's with Raveen Kumar, where you just basically have an introductory course, an advanced regression course. So yeah, if you're interested, check that out. So thank you so much for your attention.